Today I will talk about Fibonacci numbers. In mathematics, the Fibonacci numbers are Fibonacci sequence are the numbers in the following sequence 0, 1, 1, 2, 3, 5, and so on. The Fibonacci sequence is named after Fibonacci. However, it appears earlier in Indian mathematics, which is related to a kind of poetry. In mathematical terms, the nth Fibonacci number is denoted by Fn. Fn is equal to Fn minus 1 plus Fn minus 2, and F1 equals to 1, F2 also equals to 1. Or we can see F0 equals to 0, F1 equals to 1. The development of Fibonacci sequence dates back to around 200 BC, from a tally with squares whose side lengths are successive Fibonacci numbers. We can get a Fibonacci spiral that is considered as an approximation of the golden spiral created by drawing circular arcs connecting the opposite corners of squares in the Fibonacci tiling. In a Fibonacci tiling, the square has the length of Fibonacci numbers, and now we pick the opposite point of each square, and then we connect the points, we get the Fibonacci spirals. Fibonacci used an unrealistic example to explain the Fibonacci number. He used an idealized rabbit population to explain it. If two rabbits, one male and one female, are put in a field, after the first month, they are able to mate so that another pair of rabbits will be born at the end of the second month. Rabbits never die, and the mating pair always produces one new pair, one male and one female, every month from the second month on. Fibonacci questioned, how many pairs will there be in 1 year? Now he explains, at the end of the first month, there are only one pair. At the end of the second month, the original pair gave birth to a new pair, and there are two pairs. At the end of the third month, there are three pairs. Now we can see at the end of the fourth month, there are 5 pairs. So he concludes that at the end of the nth month, the number of pairs of rabbits is the Fibonacci number Fn plus 1. Fibonacci numbers also related to Pascal's triangle. In 1891, Lux represents the Fibonacci numbers by using Pascal's triangle that is used for binomial coefficients. They occur in the sum of shallow diagonals in the Pascal triangle. For example, we can see the fourth Fibonacci number 3 as in the diagonal 1 plus 2. From Pascal's triangle, Lux gives a general formula for the Fibonacci numbers, and we can see it this, where n minus 1 over 2 with blanket stands for a number I such that I smaller or equal to n minus 1 over 2 smaller I plus 1. Fibonacci numbers have many explanations, and it can be explained by the compositions of ones and twos. The most common problem is that count the number of compositions of ones and twos that sum to a given total n, and the Fibonacci number fn plus 1 means there are n fn plus 1 ways to do this. For instance, if n equals to 5, fn plus 1 as f6 equals to 8, that is, there are 8 compositions. For example, 5 ones, 3 ones plus 2, 1 plus 1 plus 2 plus 1, and so on. Fibonacci numbers can be written in many identities. If we can divide Fn into two non-overlapping groups, and one group contains those sums whose first term is 1, and the other those sums whose first term is 2, then in the first group, the remaining terms add to n minus 2, that is Fn minus 1. In the second group, the remaining terms add to n minus 3, that is Fn minus 2. Similarly, it may be shown that the sum of the first Fibonacci numbers up to the nth is equal to Fn plus 2 minus 1. That is, the summation of I from 1 to n is equal to Fn plus 2 minus 1. Superficially, the first group consists of those sums that start with 2, the second group those that start with 1 plus 2, the third start with 1 plus 1 plus 2, and so on, until the last group, which consists of the single sum where only ones are used. The number of sums in the first group is Fn, Fn minus 1 in the second group, and so on, with one sum in the last group, and the total number of sums is Fn plus Fn minus 1 plus on the way to F1 plus 1, and therefore this quantity is equal to Fn plus 2. And if we divide the Fibonacci numbers into different groups, then we can get the summation of f2i plus 1 from I equals 0 to n minus 1 is equal to f2n. And Bennett found that Fibonacci numbers are related to the golden ratio, and he gives his Bennett formula. Let phi equals to 1 plus square root of 5 over 2, and phi equals to 1 minus square root 5 of 2, then the Fibonacci numbers can be written as Fn equals to 5 to the nth power minus phi to the nth power over square root of 5. Since phi is to the negative 1 over 5, the formula can also be written as Fn equals to 5 to the nth power minus negative 5 to the negative nth power over square root of 5. Note that phi and phi are both solutions of the equations x squared equals 2x plus 1, and multiply x to the nth minus 2's power, we can get x to the nth power equals to x to the nth minus 1's power plus x to the nth minus 2's power. Then, for any values a and b, the sequence defined by un equals to a times phi to the nth power plus b times phi to the nth power satisfy the same recurrency. Un equals to a times phi n plus minus 1 plus b times 5 phi n to n. Un is equal to un minus 1 plus un minus 2. If we choose a and b such that un is the Fibonacci number, then we can find that a is equal to 1 over square root of 5, b is equal to negative 5. Kepler observed that the ratio of the consecutive Fibonacci numbers converges, and he concludes that the limit approaches the golden ratio 5, that is the limit of fn plus 1 equal to over fn equal to 5. Fibonacci numbers also can be expressed in matrix form. Now consider the linear equations. Fk plus 2 is equal to Fk plus 1 plus Fk. Fk plus 1 is equal to Fk plus 1. Let the vector Fk plus 1 equal to Fk plus 2 and Fk plus 1, and the vector Fk is equal to Fk plus 1 Fk. Then we can have vector Fk plus 1 equals to A times vector Fk, where A is the matrix 1, 1, 1, 0, and also we can get the vector Fk plus 1 is equals to A to the nth power times F0. Fibonacci numbers have many properties. Now I'm talking about the divisibility properties. In Fibonacci sequence, every case number is a multiple of Fk. For example, f5 is equal to 5, f10 equals to 55, f15 equals to 610. That is 5 divides f5n. And someone gave out the GCD of Fn and Fn equals to F GCD of M and N. And from that formula, we can find that any three consecutive Fibonacci numbers are pairwise coprime, that is, for every n, GCD Fn plus 1 is equal to 1, and so on. Also, if P is a prime, and the divisibility of P can be determined by module 5. For example, if P is congruent to 1 module 5, or P is congruent to 4 module 5, then P divides Fp minus 1. This is done by Williams in 1982, who gives the formula by using Lagrange symbol. P divides Fp minus 5 over P. Fibonacci numbers have many applications. The Fibonacci numbers are important in the computational runtime analysis of Euclidean algorithm to determine the greatest common divisor of two integers. In 2012, Brice showed how a generalized Fibonacci sequence also can be connected to the field of economics. Fibonacci sequences also appear in biological settings in two consecutive Fibonacci numbers, such as branches in trees, arrangement of leaves on a stem, and fruitless of a pineapple, and so on. That's all. Thank you.